So let's see another example of solving the heat equation. I wrote the heat equation here. It's our partial differential equation governing how heat diffuses through a metal rod of length L. This time, however, I have different boundary conditions. The partial derivative ux at location x equals 0 is 0. That means no heat can pass through the boundary at x equals 0. I can't gain heat coming in from the outside, and I can't lose heat, so it's an insulated end. Same thing for the other boundary point at x equals L. That is insulated, no heat can escape or enter through the boundaries. That's what the meaning is when I have the partial derivative here. And I also have an initial temperature distribution given by some function f of x. I've depicted one here. This will be what happens at time 0. So the method to solve this is the same as the previous video. We're going to solve by assuming that my function has a special form. It could be written as a function of t times a function of x. Then I'll place this into my partial differential equation, and then I find t prime times x equals k times tx double prime. Separating the variables, this gives me t prime over kt should equal x double prime over x. This is a function of t alone. This is a function of x alone. The only way a function of t and x can be equal is if they're both equal to a constant, which we call negative lambda. This gives us two differential equations. The first one is t prime is negative lambda times kt. The second is an x differential equation, which is x double prime is negative lambda x. And this time I'm going to put in the boundary conditions. X prime, the derivative, at 0 should be 0. And similarly, the derivative at L should be 0. Both of these we can solve. So solving one gives my function capital T equaling some constant c times e to the negative lambda k little t. Solving 2 gives my function capital X equal to, now I'm going to go on the side. I'm going to start a new page here and solve this system and write the answer here. So on the side during scratch work, I want to solve this equation. And to solve this equation, I break the situation into three cases, whether lambda is negative, 0, and positive, because in each one of those three cases, the form of the solution to the differential equation looks different. So we'll do case A, which will be the situation when lambda is negative. In this situation, the general solution to the differential equation is x double prime, x is equal to c1 times an exponential function e to the square root of negative lambda x, which of course if lambda is negative is actually a real number, plus c2 e to the negative square root of negative lambda x. Then I take a derivative. So why don't I do that? So I take a derivative to employ the boundary conditions. The derivative would be c1 times the square root of negative lambda e to the negative, or square root of negative lambda x minus c2 square root of negative lambda e to the negative square root of negative lambda x. So now I plug in my boundary conditions, and I find C1 and C2. So if I plug in 0 to this derivative, I should get out 0. So I get 0 is C1 times this constant minus C2 times the same constant. Then when I plug in L, I find 0. So that should be C1 times this constant e to this constant L minus a similar term. I have two equations and two unknowns. So you could solve these two equations and two unknowns, and you will find C1 equals C2 equals 0, the trivial solution, which I'm not interested in. So that gives me this case, just gives me the 0 solution. Boring. I don't like that case. So let's move on to case B. That'll be the situation when lambda is equal to 0. In that case, I have my function having the form c1x plus c2, because my differential equation is just x double prime is equal to 0. So I'll take the derivative and get c1. So if I plug in 0 into this derivative, I should get out 0. Thus, 0 is equal to c1. I actually do get a solution in case B, because C2 could be any number. That's fine. That's non-zero. So my solution in this case is my function is just a constant, C2, or C2 times 1. Let's see if we get any solutions in the third case. That's when lambda is positive. So in this case, the form of the general solution to this differential equation looks like C1 cosine square root of lambda x plus C2 sine square root of lambda x. In order to use the boundary conditions, I need to take the derivative. So I differentiate, and I get negative square root of lambda C1 sine square root of lambda x plus square root of lambda C2 cosine square root of lambda x. So if I plug in 0 into the derivative, I get 0. Now, sine of 0 is 0, so this term vanishes. Cosine of 0 is 1, so I get the square root of lambda C2. Now, lambda in this case is positive, so this is definitely not 0. That implies that C2 has to be 0. So C2 is 0, meaning this term is gone, that's 0. This term is gone, and that's 0. Now I'll plug in L into the derivative and get 0. So if I plug in L into this derivative, that tells me negative square root of lambda C1 times sine square root of lambda L, square root of lambda L, should equal 0. Now I don't want to get the 0 solution. I'm interested in non-zero solutions. So in order for this to be non-zero, I need this argument to be an integer multiple of pi, because in that case, sine is equal to 0. So this I need square root of lambda L to be a positive integer multiple of pi, where n could be 1, 2, 3, and so on. Thus, I know lambda is n pi divided by L squared. I do have solutions in this case C. My solutions are my function, my original x, is equal to some constant C1 times cosine of n pi over L x. So I've solved this subproblem. Now I can go back to my main problem. Here's my main problem. And I now know the solution to number 2 looks like C1, or I could get C2, well, this was C2 and this was C1 in my previous notes. It's just some constant. times cosine n pi over Lx, and this solution here required that lambda be n pi over L squared. N is a non-negative integer. So now I have my solution to this equation, I have my solution to this system. I can now write down the general solution to my partial differential equation. I have an infinite number of different solutions, one from each value of n. So I have my u of tx is equal to, now I'm going to separate the constant solution from the rest. I have a constant times, this was the case when lambda was 0, times e to the 0 power. So this constant solution was when I had lambda 0, so e to the 0 is 1, meaning I just get a constant solution here. I'm going to write it as a0 over 2, just to be reminiscent of our days when we thought about the Fourier series. Then I'm going to add all positive values of n, starting at 1 and going on. Then I'm going to write down a constant times these two things multiplied together. Again, because that was my general assumption to begin with. So I have a constant, which I'll call an, again, because that was the notation we used when we discussed Fourier series. An times e to the negative lambda, which is n pi over L squared, times kt, times the cosine function, n pi over Lx. So this is the general form, the solution that has arbitrary constants in it, but I could actually tell you what the constants are by plugging in my initial condition. So the initial condition says that my function f of x should be what I get when I plug in t equals 0 into this expression. So my function f of x is a0 over 2 plus the sum n going from 1 to infinity. Now if I stick in t equals 0, I get e to the 0 power, which is 1, so I get the coefficient an cosine n pi over Lx. Now, since 1 cosine cosine pi over L x cosine 2 pi over Lx, and so on. This is an orthogonal family. On the interval from 0 to L, the coefficients a0, a1, a2, and so on are easy to find. They're what you get from taking the projection of f onto this orthogonal family. The coefficient an is the inner product of the function f with cosine n pi over L x divided by the inner product of cosine with itself, which, if you express in integral form, would be 2 over L, again because this bottom part happens to be L over 2 when you do the integral, times the integral from 0 to L of my function f of x times cosine n pi over L x dx. So I have my final answer now. This is the general form of the solution to this system, where the coefficients are given by this integral equation here. All right, excellent.